Welcome to Tomorrow Today, where we take an inside look at how weather is impacting organizations around the world and the unique ways they're combating the impact. Brought to you by Tomorrow.io, the world's leading weather intelligence and climate adaptation platform. Hi, everyone. Thank you so much for joining us today. My name is Ruth Favela, and I'm excited to be speaking with Tyler McCandless, Director of Data Science here at Tomorrow.io. Today, we're talking to Tyler about the current state of weather modeling, and he'll do his best to educate us a bit on what makes Tomorrow.io different in the weather world. Tyler, could you start us off by introducing yourself and describing your role here at Tomorrow.io?
Of course. Tyler McCandless. I'm Director of Data Science. We do a lot of machine learning and data science at Tomorrow. My team that I lead specifically is kind of focused on improving our forecasts for our weather models with machine learning. So a lot of post-processing of weather forecasts and creating derivative products to help our customers make better decisions.
Awesome. Thanks for that background. So, to jump right in, let's start with a big question. What can you tell us about recent advances in weather modeling that are enabling more accurate forecasts?
We're at a really interesting intersection right now of advancements in high performance computing and machine learning, in observations, and weather observations, that is, and in numerical weather prediction. So, combining all those together right now, we're at the forefront of trying to combine machine learning in systematic ways to improve the weather forecasts from better observational data sets going into our numerical weather prediction models to using machine learning to predict in very short timescales with faster latency or faster predictions than what numeric weather prediction models can deliver, to outputting more accurate forecasts and probabilistic forecasts across all space and timescales.
That's really interesting. At a high level, what can you tell me about how Tomorrow.io generates forecasts and leverages data to improve that accuracy?
Really try to match the forecast challenge or opportunity with the right inputs and the right models. So if we are predicting for the US, we're going to take the appropriate high resolution models that are capturing the weather phenomena of interest. So we might use a model that's at 3 kilometer resolution, that's convective allowing and able to understand the formation of thunderstorms. We combine that with machine learning to be able to generate more accurate forecasts and probabilities from there. So you can imagine if you're an event company and you're interested in the potential for a weather event, the summertime thunderstorm, to impact your operations, we want to make sure we've trained on observations. We've married that up with the best numerical weather prediction models, and then we're generating most accurate forecasts with probabilities so that a customer can make a better decision of there's a 30% likelihood of high winds or 30% likelihood of precip above a threshold. They can make those decisions. And it's driven by that combination of the best physical models in numerical weather prediction with machine learning.
Thank you. That's a really helpful overview of that. Earlier, you said that we're using a lot of machine learning. Can you tell me about how specifically Tomorrow.io is using ML to enhance weather models?
One of the best ways that we're currently utilizing it is something that's called post-processing. So the way numerical weather prediction works is it has physical equations that govern the atmosphere that have been derived over the last many decades of scientific advancements. These numerical weather prediction models do a very good job of capturing how the atmosphere is going to evolve from its current state. But there's always biases and there's challenges with different weather phenomena. So what we do is we use machine learning to learn the patterns between how the numerical weather prediction model expects a storm system to evolve and the observations of what actually occurred historically. Then the machine learning model can tailor that, oh, there tends to be a warm bias in this area of the models, or it tends to under forecast precip in this season in this area, and ultimately producing a forecast that has the lowest error that we've quantified over a long historical record of the models as well as the observations, and generating the probabilities. Because as the forecast lead time increases, there's definitely a greater likelihood of error growth. That's going back to chaos theory. So we want to generate those probabilities with machine learning while still using a high resolution numerical weather prediction model. So that's inherently how we're using machine learning and post-processing to generate more accurate forecasts and probabilities.
That's really cool. Awesome. You're talking about probabilities. Can you explain in simple terms the difference between a deterministic and a probabilistic forecast?
Absolutely. So a deterministic forecast is we're predicting the temperature to be 34 degrees at 8 a.m. on October 18th.
Mhm.
That's a simple deterministic forecast. The probabilistic forecast is really getting at what's that full likely outcome going to be at 8 a.m. on October 18th. So it's a full distribution around that 34 degrees. And there's going to be different uncertainty in or different variability in different areas and different times of years and different locations that you're forecasting for. So the probability that we're generating is a full forecast PDF, so we can quantify that in different ways. It could be the interquartile range, which is where 50% of the observations fall. And say that for that prediction of 34, we expect 50% of the time it to be between 33 and 35. And it's a easy decision to make that more than likely it's going to be above freezing. But what happens if somebody cares about there being a 10% chance that it's below 32 degrees? We're going to show that full distribution because we're outputting multiple realizations, what we call ensemble members, of what the atmosphere is going to be. And we can compute that there is, in fact, a 15% chance tomorrow morning at 8 a.m. on that day. So that's how we're really generating probabilistic forecasts that can be used to match the decision making of our customers and really advancing the value of what weather forecasting and weather intelligence is.
Awesome. Like, what can you tell me about how showing the likely range empower business leaders to account for uncertainty when making decisions that impact their businesses?
The likely range is a really nice quantification of that relative uncertainty. So again, in that example of predicting 34 degrees, you can see that range around it. And if you're looking at a timeline for the next week and you're a gardener and you're trying to understand, am I going to bring my plants inside or not? You could see where that range, how often that falls outside of that 32-degree threshold, and give you a visual representation of, you know what, this is a week where I'm going to have to be covering my plants every night, or no, the risk is fine. It's mostly going to be above, 38 degrees, and we don't really need to take caution. So the likely range is a really nice way to get an understanding of the likely outcomes for a given forecast variable over a period of time.
That's really cool. I understand that we have customizable probability thresholds involved in our modeling. How do customizable probability thresholds allow customers to match forecasts to risk tolerance?
Yeah, instead of taking an approach of we're just going to predict certain quantiles or certain aspects of the distribution, our machine learning based model does not have a set distribution beforehand. It allows the model to learn the relationships between what's been observed and the underlying numerical weather prediction model forecast. Therefore, we generate ensemble members, or in this case, 51 potential forecasts of temperature at every hour at every given location. So with that, anybody can customize to within 2 percentage points of what the likely probability is going to be. So if there's a airline who's making a decision on de-icing, they can say above 34% likelihood that the temperature gets below freezing, they're going to have to get de-icing crews out. And then we can see how many of those 51 ensemble members are below the freezing mark and quantify the probability that way. So it's a extremely high level of customizability rather than just outputting like the 5th and 95th percentile or the 25th and 75th. That gives a good understanding of relative ranges, but here we're allowing much more precise forecasts because we're outputting each of those ensemble members.
Gotcha. From your point of view, why is displaying past forecast trends valuable for teams who are assessing reliability?
A very good question. In meteorology, operational meteorologists like to say that the trend is your friend. So when numerical weather prediction models start trending in one direction, maybe it's a snowstorm in the mid-Atlantic and the average snowfall in a given area was 2 inches, and then it became 3 inches and 4 inches. And the last model runs have been trending that way. Oftentimes, the numerical weather prediction models continue in that same direction. Not always the case, but it gives a good understanding of where that trend is likely to go. So somebody could say, oh, there's probably a higher risk of this being a higher than normal snowfall event compared to what's forecast. Another thing could be maybe there's good volatility in the forecast and the models are not resolving it really well. It's a really tricky pattern. There's multiple storm systems that are nearby, and depending on how they expect them to evolve, it has a big impact on the forecast. And someone could see that in the past trend of it seems like the forecast is trending 10-degree swings because of this uncertainty in the forecast. So it allows just another double click into that forecast uncertainty for a user to get a better understanding of the potential of a forecast changing.
Cool. Okay. Could you maybe walk me through an example of how spatial probability maps help users visualize potential geographic impacts?
Yeah, if you think about a forecast for New York City and you're looking at the specific point forecast for Newark, the airport, it's great. You can see a timeline, you can see what the forecast is, and maybe it shows that there's a 25% chance of a weather event being a thunderstorm impacting that area on that given day. But it doesn't show how the storm system is likely to evolve. And maybe there's a greater chance of storms to the north and less chance of storms to the south. Or maybe New York is just east of where the expected thunderstorms are supposed to impact, and that's why there's only a 25% chance. So when you look at a spatial map of those probabilities, you may gain insight of, well, there's actually a 90% chance that eastern Pennsylvania is going to get thunderstorms, and it would only take a shift of tens to hundreds of miles for those thunderstorms to then impact New York. So it allows for a little bit more of spatial awareness and understanding, especially for high impact events where they may be in relation to a specific point of interest that a customer has.
Yeah, and I can see how visualizing that data would be super helpful to a customer as well. We talked a little bit about the difference between probabilistic and deterministic forecasts. What can you tell me about how can leveraging probabilistic forecasts and forecast data lead to better business decision makings and outcomes for tomorrow.io customers or anyone trying to leverage weather intelligence?
The main thing is that customers and individuals all have different levels of risk tolerance. As an individual, I run every morning, and my threshold for temperature for when I need to wear a jacket is different than my wife's, and is different than my friend's, right?
Mhm.
So for me, I look at the probabilities of a forecast being below a certain threshold where I would want that jacket, and I make a different decision than somebody else would be. High impact events like de-icing for an airline, or maybe an event has a retractable roof and they need to decide before the stadium is filled if they're going to close the roof for that game or not. They're all going to have different thresholds of risk tolerance. And they may say, if there's even a 10% chance, we're going to take an action. And maybe there's an energy trader that's like, I want to know with a 90% confidence, with a very high confidence, that there's going to be a wind ramp event. And then they will execute a certain option trade. By giving that full forecast probability density function, it allows those users to customize the actions they take based on the relative probability. So really matching their risk tolerance. So I can make the right decision of wearing a jacket to run, and my wife can just wear a long sleeve. And that's how we're able to make better decisions, is customizing it to an individual's or business needs.
That's awesome. Looking forward a little bit, what innovations does tomorrow.io have in the works that you're excited about modeling for our customers? Is there anything you're excited about that we're working on right now?
There's a lot of things that I'm excited about that we're working on. We're really at an inflection point of bringing advanced R&D into operations, and that's across the spectrum from very short-term nowcasting in the minutes to hours ahead, and looking at that on the precipitation side globally, all the way out to improving forecasts and having probabilities out to 14 days. And all of these fundamentally using machine learning in various components. And then, of course, we're in space, and we're going to be even more in space, and that data is going to be extraordinarily valuable. Better data in allows for better quality models out, improving the forecast capabilities. So we're really on a literal rocket ship towards improving forecast capabilities, and machine learning being foundational to that.
Awesome. Well, thank you so much, Tyler. This has been super insightful. Thank you for educating me on how we are using machine learning in our modeling for our customers and what's to come in the future. Thank you again, Tyler, for your time and your expertise.
Thank you,
Yeah,
Ruth.
awesome.